Hello, welcome back again. So today I'm going to make another video on the quantum mechanics topic, which is a generalized Ehrenfest theorem. So there is an Ehrenfest theorem that we generally study, which relates the quantum things to the classical things. Not accurately it does, but yes, in the upper surface level, you can say that the Ehrenfest theorem connects the classical mechanics to the quantum mechanics for some extent. So in this video, we are going to discuss about the generalized Ehrenfest theorem because this particular theorem is the base of the energy time uncertainty principle. Yes, there is another uncertainty principle, which is the energy time uncertainty principle, which is not that much important, but there is a course in the Bsc quantum mechanics that yes, there is an energy time uncertainty principle. That why this is the base. And in the next video, I'm going to discuss about the energy time uncertainty principle. And this particular generalized Ehrenfest theorem is also necessary because when we discuss about the translation symmetries and different types of the symmetries and the conservation laws in the quantum mechanics, I think it's chapter number 6 in the Griffith's quantum mechanics. Then you will get to know about that how exactly there is the symmetries implies the conservation laws in the quantum mechanics. Like the translation symmetry implies the momentum conservation when the translation symmetry is a continuous symmetry and all that things. That's why this is very important to understand the generalized Ehrenfest theorem. The derivation is very short, but the equation is also very, very important for our future needs. And also when we discussed about the free electron gas, this particular topic is not directly related with the free electron gas model, but it related with the Bloch's theorem of the translation symmetry. That what is Bloch's theorem? So you will get to know about this when you study the translation symmetry when there is a discrete translation symmetry. So this is a topic of further more new videos. In today's video, our main focus is going to be on the deriving the generalized Ehrenfest theorem. So let's start our today's video. And also join my Telegram channel where I post the different types of the problems, not only from the general mechanics and electrostatic problems, also from the different branches like nuclear physics and quantum mechanics sometime. And alternate days I'm uploading the quantum mechanics questions for sure also. But my main goal was to run the channel is to understand that how the mechanics problem in the advanced level is different from the JE advanced level, how the JE advanced level of the physics questions, whether it's from the mechanics or from the electrostatics, is different from the IPHO. Because you will see the major differences between these two particular, when you see the questions between the IPHO and JE advanced questions of mechanics, let's say, then you will see the description and you will see when you understand the question, you will see that how this very difference between the questions and what the question is saying. That's why not only JE advanced question, also IPHO and INPHO, European Physics Olympiad and Asian Physics Olympiad, the questions are quite hard. I mean to say, generally very, very hard, and it takes might 2 hours to do the questions, 2 to 3 hours for a single question if you are a newbie in the physics and not studied the mechanics theory properly. So that is for another video. I'm going to tell you that in a separate video about my Telegram channel, that what's on all my Telegram channel, all that things. Let's derive the generalized Ehrenfest theorem now. So first of all, let's see what is the Ehrenfest theorem. I'm giving you homework to derive the Ehrenfest theorem, not the general Ehrenfest theorem, because Ehrenfest theorem is quite complex to derive, but you can certainly do it. You only have to write down in a proper manner to understand the notations in the quantum mechanics so that you will not get messed up. So the general Ehrenfest theorem that you study looks like this. d by dt, which is the differentiation derivative of the expectation value of momentum, is equals to the negative of the expectation value of the potential with respect to x. Expectation value of derivative of the potential energy with respect to x. So this is what the Ehrenfest theorem is. And if you have studied the classical mechanics, it means the gold standard classical mechanics, you must have seen that force is equal to the negative of the gradient of the potential energy. what is air gradient? So these are quite high mathematics. So you can visit my videos on the vector operators, and we have discussed all about that. What is the gradient, curled, and all that things. Also about the multivariable calculus. Because advanced in when you go to advanced physics, you will study the different types of the multivariable calculus also. So you can watch those videos. But for now, you can say that the force is equals to the negative of the rate of change of the potential. Gradient generally decides that how the particular quantity is changing and in which direction it is changing maximum. And this is what exactly the meaning of a gradient is. And you can imagine a situation like in a room. If you imagine a situation in a room, temperature is there. It means that every particular points in the particular room, there is a temperature assigned to it. Suppose that heater is in a one corner of the room, and there is a window, let's say, there is a window here, and if you can see that, you take the derivative, or you can say that the gradient of the temperature here, then the gradient of the temperature will compute that in which direction the temperature is increasing. So it will give you the general direction in which the particular quantity is increasing. So in this case, if the here is the heater, then the direction will like this. Okay, and if there is a window here, the direction will like this. It says the maximum increase of that particular quantity, and that is exactly the meaning of the gradient of the any particular quantity. And this is how there is a connection between the classical and the quantum phenomena, because here the expectation value is quantum, and it's equals to the derivative of the potential with respect to the x, potential energy with respect to the x. And you can say that here is the expectation value of the derivative of the potential. If you have listened carefully, then I have said that here it is not directly related that they are very connected to each other. It is on a surface level they are connected to each other. You cannot say that they are exactly connected to each other in a very good fashion. This is not true, but only for a certain extent you can say that this particular expression is true. Okay, so this is the meaning of the gradient and all that things. So this is our old Ehrenfest theorem. What is our generalized Ehrenfest theorem? So generalized Ehrenfest theorem says that d by dt of the expectation value of any of the particular observable, let's say q, is equals to the, okay, let's say we'll derive the expression. I will not force my brain to remember all those equations. Let's derive this. So if you have studied the Schrodinger wave equation, so first of all write the Schrodinger wave equation, which is the in a time independent Schrodinger wave equation, not the time dependent, because it will only lead to the complexities. So the time independent Schrodinger equation looks like this: negative of the iota h cut time independent Schrodinger equation iota h bar del psi divided by del t is equals to Hamiltonian operator psi. So this is also an eigenvalue equation. What is eigenvalue equation? You have to watch my videos on that. Okay. So here is our equation, which is minus iota h cut is equals to del psi upon del t. So if you have studied the Dirac notations, then in the Dirac notations, how we can write the expectation values. So in Dirac notations, the expectation value q is written in this particular fashion, which looks like this: psi. Here kit and brand notations. This is known as kit and brand notations. This is q. Here there will be another psi. So this is how we are going to write the expectation value of any of the observable q in the Dirac notations. So now let's continue this. D by dt of expectation value of q can be written as d by dt of, in Dirac notations, psi q operator psi. Now you have to perform some calculations. You have to operate this particular d by dt on psi, then you will operate this particular d by dt on psi, then you will operate this d by dt on this particular quantity. So let's see what will happen. This equation will like this: d psi by dt, d psi by dt, and here it will be q operator, and another psi. Similarly, in this fashion, you are going to do the product rule of the differentiation, which means this will look like this. Psi, first of all, you will do the d by dt of q operator, then d by dt of the wave function psi. So dq by dt psi, and here plus another derivation psi q d psi divided by dt. So this is our notations. Now, if you see here, then you can see that we can substitute the del psi by del t as, let's do this calculations in this particular wave equation. It will like this: del psi divided by del t is equals to Hamiltonian psi divided by h cut, and what is 1 over iota? It is negative iota. So this is how our equations look like, and we have to now substitute the value of del psi by del t and see what will happen. Substituting the values of del psi by del t as negative of 1 over h cut, and here it will be iota, Hamiltonian psi. Yes, and now here finally q and psi. Similarly, you have to leave this. You can write this as dq by dt expectation value plus psi q, then again negative of iota divided by h cut Hamiltonian psi. Now you can put down the constants out of this particular equation, then see what will happen. If I remove, or you can say that extract negative iota divided by h cut, then the equations look like this: h psi and q psi. Okay, then this particular same equations also look like, okay, put here minus negative sign, negative 1 over, or let's say iota h cut, and here it will be psi q operator h operator psi, and plus the expectation value of the time derivative of q operator. Now further what we can do is that, as you can see that in the Dirac notation, this is the complex conjugate. So if this is the complex conjugate, then the negative negative become positive, and what you are left is with this expression, which is iota upon h cut h psi q psi minus, if you convert this into this expression, it will 1 over iota h cut psi q operator h operator psi, and plus here the time derivative of the q expectation value. Now, if you have studied what is Hermitian operators, then you know that in Dirac notations, the Hermitian operators are the operator which follows this particular rule. Just suppose that this rule, that if you do the psi, then q psi, but if you reverse the order of doing the inner products, and if you reverse the order of doing inner products, and if this does not change, then this operator is called the Hermitian operator, which means q is called the Hermitian operators. And here in this particular position, this and these are the Hermitian operators. This and this are the Hermitian operators. If you convert this into the fraction form, into the denominator form, negative of 1 over iota h cut, this h psi and q the psi, if you take its, if you take this, okay, let me show you all of the steps, not be so fast. So as you can see right now, what we are going to do is that we are going to now take these some common. First of all, let's write down the full equations. This will be positive of 1 over iota h cut. There will be Dirac notations psi q operator h operator psi, and plus this similar expression, which is this. Now further we can take common the expression, which is, if I take common, sorry, 1 over iota negative 1 over iota h cut, then this expression will look like h psi q operator psi negative, this is the big negative sign, psi q operator h operator psi, then this is bracket sign, plus the expectation value of the time derivative of the q. Now this is the sign of the commutation relationship in the quantum mechanics, and I've discussed about commutation relationship a lot in the quantum mechanics. You can watch my previous video also where I've talked about the commutation relationship in a detail. So this expression looks like the commutation relationship expression between the h and the q operator. So I can write this particular expression as iota divided by h cut, negative and negative will cut out because I will take here 1 over iota is negative iota. Then this will become nothing but the commutation relationship, nothing more than a commutation relationship, which can be written as this: iota h cut h operator Q operator, and here it will be positive expectation value of time derivative of Q operator. So this is our generalized Ehrenfest theorem. It says that if this particular Q operator commutes with the Hamiltonian, it means the expectation value of Q is not dependent upon time. And this is the main feature of this particular equation, generalized Ehrenfest theorem. So this equation is also the base for deriving the energy uncertainty principle. Next video is going to be on that energy uncertainty principle, then the Dirac notations and the mathematics of the vector spaces. So for now, thank you for watching my video.